sometimes we wish to compare two or more scores that come from different sets of data. And it's difficult to do this because the scores have different means and different standard deviations. So you might want to compare two students that are coming, from two different classes or two different schools, and their marks are all they're all different, right? You can get what percentage they're getting. That doesn't really tell you the story, okay? So it says it's easy enough to nut it out if we have two scores to compare, but if we really want to compare sets of data, it's better to standardize them using a z-score. So that word standardize and the z-score go together. And it says z-score data sets always have a mean of 0 and a standard deviation of 1. And to find a z-score, we use this formula. Okay, there it is. And here's what the curve looks like. It has a mean of 0 and a standard deviation of 1. And we can kind of shove every data set into that kind of formation by changing its scores to z-scores. So here's our example. Two students, Jamie and Ruth, took a similar math test. Jamie scored 88 on a test where the mean was 72 and the standard deviation was 8. Ruth scored 91, so seemingly quite a lot better, on a test where the mean was 75 and a standard deviation of 10. Determine which student performed better using z-scores, or z. So here I go. So I'm going to do zj. Now, in the formula up there, the x is the score that's real, right? So the score that I got was 88. And then I subtract the mean, which is 72. And I divide it by the standard deviation, which is 8. Is that all right? Don't worry about the percentages. And when you do that, looks like you get 16 over 8, which is a z-score of 2. I'll tell you what that means in a minute. If we do Ruthie's score, she got 91. Oops, the mean was 75. And the standard deviation was 10. So that looks like she got, that's still 16, but over 10, so it's 1.6. All right? So these themselves are the z-scores or z-scores. This is what we're talking about. So we've standardized these now. The standardized score has a mean of 0 and a standard deviation of 1. What does that mean about a score between 1 and -1? How many are there? 68% of the scores are in here. So these two people are very bright. Okay? 2 standard deviations here is all the way over here, and 1.6 is right here. Agreed? So who did better? Jamie, of course. Okay, so it's much easier to compare when we have a z-score. So I'd say, therefore, Jamie performed better than Ruth. Easy enough? Is that on your formula sheet? No? I don't think it is. This score, this thing. X minus mu over sigma. You might have to memorize it. All right, here we go. Now I'm going to use my calculator. So it says calculate the values of the following probabilities correct to 4 decimal places. So that's a giant hint that I'm going to use my calculator in the first place. When it has a z there, that means I know already that I'm in this situation where the mean is 0 and the standard deviation is 1. So that goes with that letter. You're just going to have to know it. Okay, it's a z-score. So I want to remember here too, let's write this in really big colors. remember, okay, probability is the area under the curve. 68% of people, blah, 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 right? Okay. All right, so I'm going to go in. I want the probability, I'm going to write down here this AI. I wish I would have flinked that off, but that's okay. AI. I want the probability that the z-score is less than that. Draw a little picture, normal curve. What goes here? What's the mean? 0. 2.5 is way up here, agreed? And it's saying, what's the probability that it's less than that? So that's going to be a huge number, do we agree? Something really close to 1. Okay, so I'm going to go in and I'm going to go second vars, so dister. And all of these are normal now, so we're going to be using 1, 2, and 3 today, or really 2 and 3. So I want to go to CDF because I'm getting a big area. You never use PDF, really. It's rare. I'm going to hit enter, and it's going to say, these are so nice, what's the lower value? So what's this value down here? Well, I have negative 1 to the times 10 to the 99, but you could just put in negative 100,000, okay? Something big. And the upper score, where it ends, is 2.5. So by lower, we mean to the left, and by upper, we mean to the right. Those are already in there because it's normal. Then I hit it, and then I write this out. You could even put this, so you don't have to write a bunch of zeros. Put negative infinity. That tells the marker that you put a big negative number in there, really, really left. And then 2.5, then 0, and then 1. And does that make sense to you? 4 decimal places. That makes sense to me. It's really close to 1. All right? Okay. II. I'm going to use the same little graph here. I'll just use a different color. So I'm on II, and it says between negative 1.25 and 1.25. So somewhere between there. It's a z-score, so I know about my 0 and 1. So I go second, dister, normal, C, D, F. What's the lower? Yeah, with that negative that's down at the bottom. And the upper. And I'd write it all out with my calculator as well, but we can. Aren't these lovely? So these are really easy. And then it says convert X. Oh, we didn't do this one. Okay, B. I'm going to do B right where B is, without too much worry. So it says X is normally distributed, random variable, such that X is normally distributed. It says that. And then it says 25 and 3 squared. What is that? Yeah, it's the mean and the variance. So this is the mean, and this is standard deviation squared. So the standard deviation is 3. So it says calculate the probability that X is greater than 27, correct 4 decimal places. So I'm just going to go here. I've got this as 25 because it told me, and I've got this as 3. So that's the picture for this one. and it says, I want x greater than 27. Well, 27 is right here. Do you agree? So I want this. So what do you reckon? What's that going to be about? What did you say, 0.4? Yeah, 0.4. I don't know, something like that. Not bigger than 0.5, because 0.5 is halfway. Okay, so here I go. The lower is 27, and the upper is infinity. So I'll put a big number in there, because I want up here, greater than, and I'll put my mean in, 25, and my standard deviation is 3. And then I would write that out. That's a lie. That doesn't equal that. This equals that. Then it says convert this to a z value. Okay, the formula for the z value is c equals x minus mu over sigma. What's the x? 27. Okay, it's the x that they put in the problem, 27 minus 25, because they were trying to get this value here, yeah, on the picture, over 3. So that's 2/3, agreed? Okay, that's the z. So that's what this means. You don't have to do this. I'm just going to show you. You ready? That means if I had normalized that first, standardized it, excuse me, and I put in that the upper is 2/3, oops, the lower is 2/3, the upper is 1,000, the mean is 0, and the standard deviation is 1, because that's what z-scores are, 0 and 1, that I should get the same thing. And I did get the same thing. Okay, it just standardizes it for me. Okay, cool. Those are the questions. How long is this video?